What I want to talk about here is the intersection of two planes in three-dimensional space. Now, we've looked at the intersection of a line in a plane in 3D space, but if you imagine we've got two planes, so hold up two bits of paper, they could represent your planes. What you've got to look at is at some point they will intersect each other, and along that point of intersection, or along that area of intersection, there will be a line where the two planes will cross each other. There is only one case where this won't be, and what we're going to do is talk about these today. So if we have any two planes in three-dimensional space, as I mentioned, they've got one of two relationships. What they can be is parallel to each other, so they'll never meet or intersect each other, or they'll intersect at a line somewhere in space. Now if you imagine, I've got a couple of examples here. These examples down here, so the two red planes and these two white planes, these planes are parallel. So that would be if you imagine you had a bit of paper lying flat on the top of a desk and on the bottom of a desk. If the desk is completely flat on either side, those would represent your planes. They would be completely parallel. They would never intersect one another. They would never meet. However, if you take two bits of paper to represent your planes and just hold them in three-dimensional space somewhere so they're not parallel to one another, at some point, if you were to extend those bits of paper, they would have to meet each other in three-dimensional space. So they'd have to have some sort of relationship that looks like this diagram here, where this line here, this black line going along this bit here, represents the line of intersection between the red plane and the white plane. Now what we want to be able to do is find the equation of that line of intersection. Now to do that, we need two things. The first thing is that we need the direction vector of the line. The second thing we need is a point on the line itself. So it's our bog standard version of calculating the equation of a line in three-dimensional space. They just have to be in relation to the two planes and that line that's going to be there. Now, to find a point on the line, it must either cross the x or y plane, so that has an equation of z equal to 0, or it has to be parallel to it. Alright, there's no other way. So the line must be cross the xy plane, or it has to be parallel to it. Now if it crosses it, set z equal to 0 in both planes and get a pair of simultaneous equations to solve for x and y. Now this will give us a required point x, y, 0 on the line somewhere. If it's parallel, what we have to do is find a point xz on the plane using a similar process. We would set y equal to 0. More often than not, this is the case here, and this is what we're going to look at in our example in the next area. The second thing we have to do is find the direction vector of the line. Now because the line of intersection lies in both planes, its direction vector has to be perpendicular to the normals of both planes. So if you imagine there is one normal to a plane pointing in that direction, and there is the normal to another plane pointing in that direction. If this represented where the line of intersection was, the direction vector of that would point there, so it's perpendicular to both of these vectors. So in order to do that, what we have to do is calculate the vector product of the two normal vectors, and that will give us the direction vector of our line. Hence we'll then have enough information to be able to get the equation of that line in any of the three forms that we're after, because we've got the direction vector and we'll have a point sitting somewhere upon that line. Show you exactly what I mean. So let's imagine I'm going to ask you to find the equation of the line of intersection of the two planes given here. So x minus 2y plus 3z equals 1, and 2x plus y plus z equals negative 3. So we're going to follow the steps we discussed previously. So first thing I'm going to do is I'm going to let z equal 0. If I let z equal to 0 and substitute in, what I'll end up getting is x minus 2y equals 1, and 2x plus y is equal to negative 3. So now I've got a pair of simultaneous equations. I'm going to solve them for x and y and get out the rest of my coordinate. So if I was to do that, rearrange the top one, I get x equals 2y plus 1, and substitute it in the second one, I get 2 bracket 2y plus 1 plus y is equal to negative 3, multiply out the bracket, I get 4y plus 2 plus y equals negative 3. So if I take the 2 across here and group the y's together, I get 5y is negative 5. So y is equal to negative 1. If I then substitute it back in here, I get 2 times negative 1, so negative 2 plus 1, so I can get x is equal to negative 1. So what I can then say is that the point on the line that I'm going to use is going to be equal to negative 1, 0. So I'm going to take the point on that plane there. What I'm then going to do is I need to find the normal of the two planes and take the vector product of it to get the direction vector of my line. So what I'm going to do is, if we just call n1 the normal of the first plane, so this one here, just by inspection I can look at it and say that that's 1, negative 2, 3. And let n2 be the normal of the second plane. Again, just inspect it, looking at it as 2, 1, 1. If I then take n1 cross n2, put it in a wee matrix like my I, my j and my k, plus, minus, plus, what I'll end up getting is 1, negative 2, 3, 2, 1, 1 here. So from that, what I can say is if I do the rows and columns again, so for my I, I'm going to get negative 2 times 1, take away 1 times 3 in the I direction. Then I'm going to get take away 1 times 1 going across here, take away 2 times 3 in the j direction, and I'm then going to get plus for the k direction, 1 times 1, take away 2 times negative 2. So I'm going to get 1 take away 2 times negative 2 in the k direction. Simplify all of these out, and what I can say to you then is the vector product will give me a direction vector, so negative 2 minus 3, so negative 5i. It's going to be the minus 5j, so plus 5j. And what I'm then going to get here is 1 minus 4k, so plus 5k. And if I write that as a column vector, it's negative 5, 5, 5. Take it the 5 as a scalar multiple, and my direction vector is going to be negative 1, 1, 1. So this here is the direction vector in its simplest form. This 5 multiplying it, so the negative 5, 5, 5, is just a scalar multiple. We can break it down to the most basic of it and have it as a negative 1, 1, because that's still going to give us the direction of it. The 5 times it just tells us a scalar multiple of it, so it's just stretching that direction vector out and just making it bigger. We want the most fundamental part of it, which is going to be given here. One point to note quickly, actually, before I go on to do the equation of the straight line, is I could have taken the negative out with it and put negative 5 out front and had it as negative 5, bracket 1, negative 1, negative 1. Either variation of this is fine. To be honest with you, I would probably take the negative out to get rid of it and just reverse the sign, so I'm going in this positive direction with x. But again, it doesn't matter which of the two ways you use, you'll still get the same direction. You'll still get the same equation of the straight line. All it will change is the signs on the bottom because of the direction you're pointing. Either way, when you put them all together in the formula for the equation of a line in three-dimensional space, I'll use this one here to do it. What I'll get is I'll get x plus 1 over 1 equals y plus 1 over negative 1 equals z over negative 1. If I use the other variation, all of it changes the signs on the bottom for it. So it's actually a fairly straightforward process. It's just remembering that we need those two key bits of information. As we would for any line in 3D space, we need a point on the line, direction vector on the line. Getting the equation of the line doesn't change. None of the steps for that change. They are all the same. We just have to work it through from there once we get the info we need.